Good morning, everyone. So today we are going to continue what we started yesterday. We will just start with a quick review of, oh wait, let me, now I can hear people on Zoom because I muted my laptop. As I was saying, we will start with a review on what we covered yesterday, vectors and scalars, which is section 2.2 in the book. Then we will cover time, velocity, and speed, which is section 2.3. And then we will start a new topic, which is acceleration. I touched on it briefly yesterday, but really, I didn't say anything except the definition. Then we will write down the kinematic equations for one-dimensional motion. I'm not sure I will prove them to you today. If I didn't, I will just state them, and tomorrow I will prove them. But we will use them extensively in the activity that you will be doing today. This is the activity that you will be doing today for the rest of class time. I will upload it to Canvas once we get started on it, but for the first half of the lecture, we will just not be doing the activity, okay? So let's start with our review. Okay, so as we said yesterday, a vector is a quantity with both magnitude and direction, whereas a scalar is a quantity with only magnitude. So a vector is a quantity with both magnitude and direction. And examples include displacement, because we covered displacement last time. And it was a vector, and the direction of the vector in one dimension was either a plus or minus, meaning to the right or to the left. That's all in 1D. In more than one dimension, you can have it pointing at an angle, like 45-degree angle, or pointing east, west of east or something, west of north or something. So displacement is a vector. Also, velocity is a vector, as we will talk in a minute. Acceleration is also a vector. Forces are vectors. If you go a little bit more advanced, or as you will see in 42, whoever will take the class, electric field is a vector, magnetic field is a vector. So we have lots of vectors in physics, okay? A vector is a quantity with both magnitude and direction. Whereas a scalar is a quantity with magnitude only. No direction. Examples include distance, speed. You can also have temperature. Yeah, that's enough for examples. Okay, and as we said, a vector in 1D, plus sign means to the right, and minus sign means to the left. And this is convention. You can flip that convention as long as you're consistent. So you can define your positive to mean left side instead of right side, but often most of the time we define positive to be to the right. Okay. So yesterday we defined displacement as the change in position, and we already defined what position is. We defined what the coordinate system is. So now we can define what time is, and from there we can define what velocity is. So let's start by a definition of time. And as we said, time is a fundamental quantity, so it cannot be defined, it can only be defined by stating how you measure it, okay? So time So let's say time is defined as change. You will not know if time has passed if nothing has changed. Like you have to have some physical quantity change, right? So for example, the position of the sun in the sky, this denotes time. The position of the pendulum, if it's experiencing periodic motion, even a heartbeat can indicate time, right? So you can count your heartbeats and each one of them associate with a unit and call it second or part second or something. But there has to be a physical quantity that's changing, and this is how we define time. So as a change of a physical quantity, let me just be explicit, as a change of some physical quantity. Then we can define a mathematical quantity as the elapsed time, which is simply just the difference in your like stopwatch. Like if you look at the clock now, it's 8:16, and if you look at it 2 minutes after, it will be 8:18. So you subtract the final time from the initial time, and this is the time elapsed between two events. As usual, we denote it by delta t, which is the change in time, because that's really what's physical. The time itself, if we denote some event by a number, it's arbitrary. We can call the day as the 0 point or the origin, and then any time before will be negative, and any time after will be positive. But we only care about the difference between two events. So delta t is defined as the t final minus t initial, and it's much simpler to just define your start of event as the 0 time, and then just say, instead of writing delta t, just define that as t. So t will be the time elapsed between two events, okay? Okay, now we have displacement and we have time, so we can go on and define velocity. So velocity, or let's start with average velocity first. Average velocity, let's denote it v with a bar on it. It is defined as the change in position, which is displacement, over the elapsed time. So it's final position minus initial position over final time minus initial time, or simply just denote the denominator as t. Okay, so this is the average velocity. And you can see from the definition that velocity is a vector because displacement is a vector, and the time elapsed is a scalar. So it's derived from a vector. So velocity itself is a vector. It has both magnitude and direction. But then the average velocity doesn't really tell you much about what happens between two positions. It only tells you the average. For example, if I walk from here to the end of the room and stopped for a while and came back, the average velocity doesn't tell me anything about that. The only thing taken into account here is the total time. So if I stop for a little bit, the time gets larger and the distance is the same. So it will indicate less speed, less average speed, but it doesn't say anything about what happened in between. So if we wanted to have more details, we will make our time interval smaller and smaller and smaller until eventually it becomes infinitesimally small, practically a point in time. So this defines instantaneous velocity, not average velocity. So instantaneous velocity is the average velocity, but over a very small amount of time, or effectively at a point or a moment in time. Instantaneous velocity. I will denote it V without a bar. And this is the average velocity over an infinitesimally small amount of time. Over an infinitesimally small amount of time. And mathematically, we can write that as delta t goes to 0. We will not use that. It's a calculus notation, but it's just that's what it means. We take the limit as the time becomes infinitesimally small. And the instantaneous velocity is what tells us about the details in the theory. So let's take an example on average velocity. Let's say this is your home and this is the grocery store, and you drive to the store and return in half an hour. So the time elapsed between you going to the store and coming back is half an hour. So we start by writing our unknowns. And the distance between your home and the store is 3 kilometers. Okay. So as always, since this is a coordinate system, we denote the origin. Let's denote the origin as your home. So x equals 0 will be your home, and x equals 3 will be the store. These are just the marks on our ruler. And if we wanted to calculate the average velocity, we need to first calculate the displacement, right? Because average velocity is displacement over time elapsed. So let's calculate the displacement first. Displacement is defined as the final position minus initial position. So in that case, if you go to the store and back, what is x final and x initial? Can anybody guess? Yes, it's 0 for both. Because you started and returned to the same point. So it is 0 minus 0, so it's essentially 0. So when you calculate the average velocity, which is delta x over delta t, you get a 0. So the average velocity is 0. So as you can see, it doesn't tell you anything about what happened in between. If you just stayed there, didn't do anything, it will also be average velocity of 0, as long as you're at the same point. So let's now define the speed. And in the same way we define displacement versus distance, we will define velocity versus speed. So speed is defined as the total distance traveled this is actually the average speed. Total distance traveled between 2 points. I already used delta x for displacement, so I don't know what to use for total distance traveled. I will just write it down over total time elapsed. So in the store example, what is your average speed in the store example here? What is the total distance traveled first? Yeah. So you go for 3 kilometers and then you come back for 3 more kilometers. It doesn't matter what sign the displacement is because it's the distance we're concerned about. So this is 3 kilometer plus 3 kilometer. This is the total distance traveled over half an hour. So this is 6 over half. So this is 12 kilometers per hour. So this is the average speed in this example. Okay. It still doesn't tell you much about what happened in between because if you waited for a long time in the store itself, like you're not moving or doing anything, you will get less and less average velocity, even though the actual distance you covered it in less time, but the average speed doesn't take that into account. So as the instantaneous velocity case, we also have the instantaneous speed. Which is defined the same way. You also take the average speed and make that average over an infinitesimally small amount of time. So I will just define the same way as instantaneous velocity. Okay. It's important to notice here that the average speed is not the magnitude of average velocity, because as you saw above, average velocity was 0, but average speed was 12 kilometers per hour. So they are not the same, but the instantaneous speed is the magnitude of instantaneous average velocity because you take the average over an infinitesimally small amount of time, so all these differences disappear. But for averages, average speed is not the same as average velocity. Okay, so now let's move on to acceleration. 2.4. Okay, so in everyday conversation, when we say something is accelerating, we're saying something is speeding up, right? And when you have more acceleration, you are increasing in speed over a smaller amount of time. This is consistent with the formal definition that we will have today. However, the formal definition is more inclusive because acceleration can be positive or negative. Acceleration could slow down an object, not just speed it up. And depending on what direction it has with respect to velocity, it will determine whether it will speed it up or slow it down. So let's write the mathematical definition first. So acceleration is denoted by a small a with this is average acceleration first, average acceleration. Average acceleration A bar is defined as the change in velocity over change in time. So this is just V final velocity minus initial velocity over the time elapsed. Okay, this is the mathematical definition. And as you can see, again, acceleration is a vector quantity because velocity is a vector quantity, and velocity is a vector quantity because displacement is a vector quantity. So it all follows systematically from one another. So, so acceleration is a vector. And as for instantaneous velocity and instantaneous speed, we also have instantaneous acceleration, which is average acceleration defined over an infinitesimally small amount of time. So we have some conceptually important notes here because velocity is easy to imagine. Displacement is also easy to imagine or visualize, but acceleration becomes tricky in some situations, especially because the everyday notion of acceleration means speeding up. So let's clarify that by some examples. So conceptual note. Acceleration from the definition is in the direction of the change in velocity, not the velocity itself. So velocity is in the direction of motion. We're moving this way. This is the direction of the motion. But the change in velocity can be opposite to the change of motion. And this is if we're slowing down, for example. So acceleration is in the direction of change in velocity. Not velocity itself. We can write down some examples. So if we have a car here moving on a straight line, let's say this is the direction of the velocity, and this is the direction of acceleration. In this case, as we said, conventionally, we will define the right-hand side to be positive. So in this case, we have acceleration is positive. This is a long word. I'll just denote it like this. Acceleration is positive. And the car is speeding up because acceleration is increasing the velocity. The change in velocity is in the same direction as velocity. So you increase the velocity that you already have. And in the other case, we can have same car moving this way, but acceleration is this way. Okay, so here acceleration is negative, and car is slowing down, or we say it's decelerating. And this is where it comes tricky because usually when we first get introduced to this concept, we think negative acceleration means deceleration, which is not correct. So it's not always the case that when acceleration is negative, the object is slowing down, because if you think about an example like this, let's assume the car is moving to the left. So this is the direction of velocity, and this is the direction of acceleration as well. So here acceleration is negative, but the car is still accelerating, like speeding up to the left side. So negative acceleration could just as well mean speeding up. It doesn't have to do with deceleration. These are different notions. And this is because the definition of positive and negative is arbitrary. Actually, we just chose positive to be to the right and negative to be to the left. We could just as well flip it and say to the left is my positive. And the final case is that we can have the car moving this way and the acceleration is this way. So acceleration can be positive and still the car is decelerating. Whenever I say decelerating, that will mean slowing down instead of just acceleration being positive or negative in that confusion. Deceleration always means slowing down, whether it's to the right or to the left. Okay. So from these pictures, we see what's important is not the sign of the acceleration, it's actually the direction of acceleration with respect to the direction of the velocity. If acceleration and velocity are in the same direction, like this one and that one, the object is speeding up. The speed is increasing. And if they are pointing in opposite directions, like in these two cases, the object is decelerating. Okay? So the speed is getting lower and lower. So you have to be careful when thinking about what positive and negative mean, because positive and negative is just a mathematical construct, but it's not physically realizable in nature. What's physically realizable is the direction of acceleration with respect to velocity. Okay, so these were just some important conceptual distinctions to notice or not get confused. Okay. Okay, now let's take an example that reviews all what we covered so far. So, and this is a combination of a couple of examples in the book. It's examples from 2.2 to 2.8. It's a combination of all of them, but I will just condense it into one example. We have two scenarios. First scenario is a subway train going this way. This is the direction of motion, which is the direction of velocity as well. Okay. So the initial position is 4.7 kilometers, and the final position is 6.7 kilometers. By the way, is this color? Can you see it? Okay. So we want to calculate displacement, average velocity, average speed, acceleration, and everything we know so far. We will calculate it once for this case. Let's call it A. And one more time for this case, but you will do the other case where the train is going this way. Starting from x naught equals 5.25 kilometers to x final being 3.75 kilometers. Okay. So I will do part A and you will do part B. Uh, let's do part A. So first we want to calculate displacement. So displacement is defined as the change in position. So delta x equals to x final minus x initial. And in this graph, since it's a vector, the arrow is pointing this way. Okay, to the right. So we expect it to be a positive number. So delta x is 6.7 kilometers minus 4.7 kilometers. This is 2.1 kilometers. Then the distance traveled is just the magnitude of the distance covered. So it's also equal to 2.0 kilometers. Now we will assume that the train moves for okay, so assume the train was moving with, yeah, I have to have more inputs here. So assume the velocity of the train when it was moving to the right. The initial velocity was 30 kilometers per hour, and it will stop. The final velocity is 0. It stopped. And that happened over a time interval of 20 seconds. And we want to calculate the average velocity in that case. We want to calculate the average velocity, average speed, and average acceleration. So to calculate average speed, average velocity, sorry, we only need time and displacement, right? Delta x over delta t. We calculated the displacement above, it was 2 kilometers, and the time is 20 seconds. So 2 kilometers over 20 seconds. And just, we don't want to have mixing units, so we will convert the units to kilometers per hour. So this is 2.0 kilometers over 20 seconds. We multiply that by conversion factors, as we learned last time. So there are 60 seconds in 1 minute, and there is 60 minutes in an hour. So as usual, the units cancel, and we only get kilometer per hour. So when you calculate that, it's so it's 2 over 20 times 60 times 60, and this is in kilometers per hour. Yeah, you can calculate that. My mind is not working to calculate it. But yeah, it's just plugging it for the calculator. This is the average velocity. I guess this will be 360 kilometers per hour, if I'm not mistaken. Okay. The average speed in this case will be the same because the distance traveled is 2 kilometers as well, because it didn't, the train didn't return or do any any going back and forth. It's just this distance is the same as average velocity in this case. Now we want to calculate the average acceleration. And from the definition, it's change in velocity over change in time. And we said that it starts at 30 kilometers per hour and it stops at velocity equals 0. So the average acceleration is final velocity minus initial velocity over time, which is 0 minus 30 kilometers per hour over 20 seconds. Again, you do the conversions to have it in kilometers per hour squared, but this is not a conventional unit, so we will write it down in meter per second squared. So this is negative 30 over 20. Then we have kilometer per hour, and we have seconds here. So we want to get rid of the hours and kilometers. So to get rid of kilometers, we multiply by 1,000 meter, divide that by 1 kilometer because they're equivalent, and multiply by another conversion factor for hours. So 1 hour has 60 minutes and each minute has 60 seconds. So this is just 3,600 seconds in an hour. So as usual, units cancel. And we only get numbers in meters per second per second. So meter per second squared, which is the unit for acceleration. So this is negative, again, you can calculate that. 1,000 over 3,600 meter per second squared. I guess I calculated it somewhere here. Yeah, this is negative 0.417 meter per second squared, or meter per second per second. This is the average velocity in this case. And in this case, the acceleration is negative, meaning that it is pointing to the left. And if you remember, the train was moving to the right. So the acceleration to make it stop is pointing the other way. So it's decelerating the train. If instead I told you it was starting from rest, so the initial speed or initial velocity was 0, and it accelerates up to 30 kilometers per hour, we will get the same number, but with a positive sign, because it's speeding up from rest to arrive at that acceleration, to arrive at that velocity. Okay, I want you guys to do the part B for this case. Do the same thing. Get the displacement, distance traveled, average velocity, average speed, and average acceleration. But I have to tell you what the time taken is, the time elapsed, and the initial and final velocity. So let's say it starts from rest. So starts from rest and reaches speed of let's also make it 30 kilometers per hour. Be careful, because here I told you it reaches a speed, but it's moving to the left, so the velocity would be negative. So, make sure you take you take that into account. And that happens in a time of 8 seconds. Okay, I want you to calculate everything. Take 5 to 10 minutes, and then we will continue. Okay, so I will write down the final answers for the question and see if you guys got the same answer. So for displacement, Uh, I just need a little bit more space, so I will move this. Here. So displacement was negative 1.5 kilometer. Okay, because it was to the left. So the direction of displacement vector is to the left in this case. Distance traveled is positive 1.5 kilometers, because distance is magnitude, it cannot be negative. Average velocity in that case is just dividing displacement by the time interval taken, and that will be negative as well. This is negative 675 kilometer per hour. Okay, is that what you guys got? Okay, then average speed is positive 675 kilometer per hour. And finally, average acceleration was negative 1.04 meter per second squared. Okay, so even though the acceleration is negative in this case, the train starts from rest and speeds up. Okay, so this all makes sense now. So this is all we covered so far. The next topic is to get the equations of motion for objects moving with constant acceleration before giving you guys the activity to work on. By the way, when do you want to take a break? Do you want to cover kinematic equations first and then take a break and come back, or now and then? What's your preference? Keep going. Okay. So section 2.5. Kinematic equations in one dimension. Okay. So far we've defined displacement, velocity, and acceleration. We've defined average and instantaneous for every case. So let's just simplify our notation a little bit. So we had delta x being x final minus x initial. Okay. Instead of writing it as x final, we will write it as just x. So I will just write it as x at any moment of time. This is a function notation. Okay, so this is the position at a time t. So then delta x becomes just the position at time t minus the initial position that I have. Okay. And I will do the same thing for velocity. So the change in velocity is velocity final minus velocity initial. I will write down velocity final as velocity as a function of time. Then delta v is, actually I can rearrange that. I can rearrange that. So from here, we can write down x of t as x naught plus delta x. Like the position at any moment of time is the initial position that you started with, and you add on it the displacement that you've covered. Okay. Then we do the same thing for velocity. Denote velocity final as velocity as a function of time, and then velocity as a function of time is initial velocity plus the change in velocity. Okay. And finally, we actually did that above, but we have delta t equal t final minus t initial, set t naught to 0, then you just have delta t being t, column t final as t. These are just simplified notation. So when we write down the equations of motion, we don't have to write f and naught every single time. Okay. So let's start with the definition that we had for the acceleration. So we had average acceleration being delta v over delta t, right? So change in velocity over change in time. So I will write that down as v of t minus v naught, as we just said, over t. Okay. By rearranging that equation, we can multiply both sides by t, so we get a bar t equals v of t minus v naught, and then by rearranging that, we get v of t equals v naught plus a bar t. This is the first kinematic equation. This is a very important equation that you will keep using throughout the kinematics. There is an important assumption that we can make here, that assume acceleration is constant. Assume constant acceleration. And what that means is instantaneous acceleration is just the same as average acceleration, right? Because acceleration is not changing, it's constant. So when you average it over time, it's still the same. So instantaneous acceleration which is denoted A without a bar, is the same as average acceleration. Okay. So the kinematic equation now can be written down as V naught equals V naught plus AT in the case of constant acceleration. And just as a sanity check, an important habit to have is that you always want to check the limiting case. For example, here, if you assume acceleration was 0, you're not accelerating at all, then the velocity at any moment of time will be just v naught, the initial velocity, because the term that has acceleration vanishes. So no acceleration, so you just have the same velocity over and over. Okay, so the equation kind of makes sense. And you can also check that if you have acceleration, if you're moving to the right, then velocity will have positive sign. So then if acceleration is also to the right, which is positive, you will keep accumulating positive numbers to the right-hand side. So the left-hand side will get bigger. So that means your velocity is increasing. So this is just interpretation of the mathematical equation that you have at hand to explain the intuition you have. Okay, this is just a sanity check. This is, I will call this equation 1, because this is the first kinematic equation. Now let's derive the second important, very important kinematic equation. This gives us velocity at any moment of time. We want an equation that gives us the position at any moment of time. So we have defined the change in position or displacement as, actually we defined velocity, average velocity, as the change in position over change in time. And we said this is equal to position at any moment of time minus initial position over the time elapsed, right? which can be rearranged as we did above, as we can multiply both sides by t, and then move the x naught to the other hand side. So x t minus x naught is equal to v bar t, and from that you get position as at any moment of time is the initial position plus the average velocity times time. Now, we don't want it to be expressed in terms of average velocity. We want it to be expressed in terms of acceleration, because the parameters we have in the kinematic equation are position, velocity, time, and acceleration. And since acceleration is constant, this will be given to us in any problem, or we will calculate it. But this is assumed to be constant, so we need to express our equations in terms of acceleration, not average velocity, because as we said, average velocity does not tell us information of what happens in between two positions. So we need to eliminate this v bar in favor of acceleration. So let's move this equation around here to start with. The average velocity is what in terms of initial and final velocity? If we wanted to write down the average velocity, what is it? What's the statistical average of a quantity? Any guess? So the average velocity is the initial velocity plus the final velocity, and then you divide that by 2. Right? So this is how you define a statistical average. And it's the same thing if I tell you I'm 24 years old and you're 26 years old, so our statistical average is 25 years old. So you add the two ages and divide them by the number of events or number of people. Okay. So this is initial velocity plus velocity at any moment of time divided by 2. Then I will substitute that here. So I will take that and substitute it here for v bar. Okay. You will not have to do any of that when you're solving problem. I'm just deriving the equation for you. And once we get to the equation, this is all you need. So now we will have x of t equal x naught plus v naught plus v of t over 2, all of that in brackets, multiplying time. We can do some algebra here. So x naught plus v naught t over 2 plus v of t times t all over 2. Okay. And we will take the equation that we have derived above, which is equation number 1, and substitute it for v of t here. So substitute v of t from equation 1. So I will write it here, just actually let's pull it down here. We have, this is v of t. So we will substitute that here. So this now is x of t equal x naught plus v naught times t over 2 plus v naught plus at times t over 2. Again, some algebra. So x naught plus v naught t over 2 plus v naught t over 2 plus a t squared over 2. These two terms are the same, so half v naught t plus half v naught t, so that gives us v naught t. And we get the final equation that we need to arrive at x of t equal x initial plus v naught t plus half a t squared. This is one of the most important kinematics equations along with the first one. Okay. These are really important. You will use them a lot. There is a third important equation. It is not fundamental. It's derived from these two. You can eliminate the time from one equation and substitute it into the other equation to get an equation that has only position, acceleration, and velocity. So if you're accelerating and knowing your acceleration and initial velocity, you can get your final velocity if you know how far you are going. We can derive that. Actually, let me derive that to you next time. But for now, let's write it down. So I will write down all equations on top of each other, just to have them with you when you're doing the activity. So kinematic equations, 1D kinematic equations. One V t is equal to V initial plus acceleration times time. 2 x of t is x naught plus v naught t plus half a t squared. And 3, which is not proved yet, is that v squared is a function of time is equal to v initial squared plus 2a x minus x naught, or I will just write it down as delta x, like the distance traveled or the displacement. Okay, so this one derivable from 1 and 2 by eliminating the time variable. Okay. And those are only in the case of constant acceleration. If acceleration varies, then these equations don't hold anymore. Okay. These equations are functions of time. So we can think of position as a function of time, velocity as a function of time, acceleration as a function of time as well. I will not discuss graphs a lot today. We will have a separate lecture for them, but let's just touch upon it briefly before giving you the activity. So if an object is moving with constant acceleration and we want to draw an acceleration versus time graph. So let's put the time on the x-axis. Usually the independent variable is placed on the x-axis or the horizontal axis, and the vertical axis is reserved for the dependent variable. That it, like when you change the independent variable, you see what the quantity corresponds to. So if we want to draw acceleration versus time for a let's say it's for a car moving with constant acceleration. Right, so this is the car, and this car is moving to the right with constant acceleration. Okay, and this is the x-axis, just the line of motion. And let's say this acceleration is equal to 10 meters per second squared. Since it's a constant acceleration, if you look at it at time t equals 0, it's 10. If you look at it at one time, it's 0, 1, 2, 3, etc. If you look at it at 2, it's still 10. At 3, it's still 10. So when you connect all the dots together, the acceleration graph is just a straight line at 10 meters per second squared. If you wanted to plot velocity as a function of time, then you will have a similar graph, not similar to acceleration, but same way of generating it. So during moments 1, 2, 3, 4. Since there is acceleration, there is increase in speed in that case, because it's positive acceleration in the same direction of velocity. If we assume the object starts from 0 velocity, then at time equals 0, the object is here. The car is here at the 0 velocity, right? And from the first kinematic equation, we will have velocity just equal to AT. If it starts at 0 velocity, which if you look at it, it's just the equation of a straight line with a slope accelerated from algebra. We will discuss that in detail, but for now, just it's 10 times t because the acceleration is 10. So at t equals 0, v is 0. At t equals 1, acceleration velocity is 10. At t equals 2, velocity is 20. And when you connect the dots, you get a straight line like this. At 1, it's 10 meters per second. At 2, it's 20 meters per second. And this graph, the slope of velocity is the acceleration. If you want to draw position as a function of time, then again, look at the kinematic equation, number 2. We have initial velocity equal to 0. So the second term vanishes. We can assume it starts at position equals 0. It's just the definition of the origin. So we can place the origin at the beginning of its motion. So the position function will be x of t equals half a t squared and acceleration is 10, so 10 times half times t squared, so this is 5t squared. And again, 1, 2, 3, 4. At t equals 0, position is 0. At t equals 1, this is 5. At t equals 2, 2 squared is 4. And then this is 20. And when you connect the dots, you get that it's a parabola. So it's curved like that. Okay. So this is how we can think of kinematic equations as graphs. And the slope of position versus time graph gives you velocity, and the slope of velocity versus time graph gives you acceleration. We will see later on that the area under the curve of position versus time, velocity versus time graph gives you position, and the area under the curve of acceleration versus time gives you velocity. So we can go back and forth between these quantities mathematically using graphs. Okay. This was just a brief introduction to graphs before discussing it in depth next time, because tomorrow in the lab, you will work with motion detectors and cars and carts. And on the computer, what you see are graphs like this. Okay, because you move your hand like this is a physical motion, but if you move it so fast, you see the velocity graph goes up. And if you move your hand far away from the detector, you'll find the position versus velocity, the position versus time graph goes up. So this is just a warm up for tomorrow's lab. Okay. Okay, now I will give you the activity. I haven't uploaded it to Canvas yet, so let me do that now. Oh, I have a message in the chat. I didn't. Yeah, I haven't seen that. Benjamin, are you still there?
Yes, I'm here. Sorry.
What equations you wanted me to scroll back? I'm
No,
very sorry.
I'm actually fine. Sorry about that.
You guys want to take a break or work on the activity and then take a break? Okay. We will keep going. Okay. Okay, can you guys check Canvas now to see if it's there, if you can see it? Guys, can you hear me on Zoom? Please confirm if you can see it on Zoom. Zoom is up, as I can see under module here, in class activity 1. Guys on Zoom, can you form a group, please? Like you can work together and submit your work individually, but only one paper will be graded for feedback. Okay?
Okay.
Also, if you have any questions, just let me know. If you typed in the chat and I haven't responded, just shout at me, okay? Yes, I should put you in breakout rooms. Let me see how to do that. Breakout rooms. Two breakout rooms. Okay, assign automatically. Yeah, I'm the seventh, so that okay. Open all room.